Wolf here, and in this video I'm going to be introducing using LOL graphs to help us set up our equations, our energy equations. So in this packet, what I would have liked you guys to do first is complete pages 3 and 4. These are just some real quick, easy, nice drills to practice our equations. The key, by the way, is on Canvas, so make sure to check that out before you go on to integrating all these equations with the more complex critical thinking LOL diagrams. Okay, so let's look at an example problem. A 0.1 kilogram toy is traveling 1 meters per second down a frictionless ramp. So for me, I always like to visualize what I'm reading. So instantly, I'm going to maybe say, okay, I have a ramp. So I don't have a lot of space here. So maybe up here, I'll just draw a ramp. And I'll draw my card at the top of the ramp. It says its mass, or it's 0.1 kilograms, which I know that unit's for mass. So it's 0.01 kilograms. And it rolls. It's already initially traveling, so I could say my initial velocity is 1 meters per second. I always like to maybe just put like a little arrow here too, just to kind of show that it does have some velocity initially. And it starts from a height of 0.3 meters, so I can label that as well, above the tabletop. And the question is how fast will the car be going? Sorry, that's my alarm. How fast will the car be going at the bottom of the track? So what I'm looking for is my final velocity. All right. So in order to solve this problem, to kind of look at the before and afters and organize everything, it's helpful to make these LOL diagrams. Right? Just kind of visualize what energies we have. So the first thing I'm always going to ask is, in my initial and final situation, is the object moving? And if it is, it has kinetic energy. And if it does the object have height? And if it does, it has potential energy. So initially, right, I'm at some type of height, so I could put UG down. And I have some type of velocity, so I definitely have kinetic energy too. So you might be wondering, why did you how'd you know to make these blocks right here for kinetic and potential energy? For our purposes, for right now, we're using this model to just help us visualize what energies are present. So you could have easily said, oh, there's 2 kinetic energy and 1 potential. Or you could have said that there's the same amount. Or you could have said that there's actually more potential. All right? As long as you have kinetic and potential energy, you're good. So I'm going to leave it like this. Now here's the important thing. Even though I got to decide how many blocks there are initially, if I have 5 total, right, due to the law of conservation of energy, that energy can't be created or destroyed, I know that I have to have 5 total energy blocks over here as well. So if I look at my final situation, I'll say, do I have a height? No, I'm on the ground, so nothing for UG. And then I would definitely be, if that's the case, kind of intuitively I know that I would be moving, but since energy can't be created or destroyed, I know that that potential energy here was transformed into all kinetic energy. So I'm going to draw 5 blocks for kinetic energy. All right, now the whole purpose of making these LOLs is to help us make an equation. So in general, our, let's say, mechanical energy initially, there's not a lot of space for this, is going to be equal to our mechanical energy at the end. All right. Now the nice thing in our situation, since this is a frictionless ramp, early on we're not going to worry about what's happening here in terms of forces acting on our system. So energy transfer is just going to be 0. So we're really just comparing the initial and final energies, right? Total energy initially has to equal the total energy final because energy has to be conserved. So then I'm going to start writing my equations. I know I have kinetic energy plus potential energy, which I know I have, is going to be equal to, and I'm just going to put kinetic energy here because that's the only type of energy that I have. All right. So the problem is asking, though, for me to find my final velocity. And velocity is clearly not in any of these energy variables. So what I have to do is I have to expand this equation out. I know that the equation for K is 1/2 mv squared plus potential energy, which is mgh. All right. 0 is still here. And then kinetic energy is 1/2 mv squared. So this value right here, that's the value I'm looking for, my final velocity. So now I'm just going to start to substitute numbers into my equation. I don't think there's enough space right here, so I'm going to do everything just like underneath. So if I do 1/2 times the mass, which is 0.1 kilograms, times the initial velocity, which if I go back up here is 1 meter per second, squared, plus my mass, which is 0.1, times g, which is the gravitational field strength, and if I'm on Earth, that's 9.8. And then my height is 0.3 meters. So I'll put that in. Right, and that's my initial energy or total energy, and that's going to be equal to my final total energy, and all my energy at the end is in kinetic energy, so 1/2 0.1 for my mass. Velocity is what I'm looking for. All right, so now I just have to solve. So if I do 1 squared is 1 order of operations, always square this first. So 1 times 0.1 times 1/2 will give me 0.05 plus 0.3 times 9.8 times 0.1. You could have done the other 0.1 times 9.8 times 0.3 would give you 0.294. All right, 0.1 times 1/2 gives me just 0.05. And then that's multiplied by velocity squared. So I'm going to combine these two variables right here. 0.05 plus 0.294 gives me 0.344. And that's equal to 0.05 velocity squared. I'm just kind of doing this one step at a time. I'm going to make sure to divide 0.05 by both sides. Right, so then it ends up being 0.344 divided by 0.05. And that'll give me 6.88 is equal to velocity squared. Now I want velocity on its own, so I'm going to take the square root of both sides, and my final velocity is going to be 2.62 meters per second, which in this case we give you the answer. So you kind of know what you end up, what you know what you have to end up with after setting up all the problems and everything. All right. So a few things. This might look kind of complicated, but it's really just a longer algebra problem. And to tell you the truth, this is a very small percentage of the physics, this bottom part. All right? The physics, I think the stuff that makes this most difficult is identifying the energies and making our equation from that specific scenario. And so the LOLs are really, really, really helpful for getting started with writing your equations, expanding, and eventually solving. Thanks for watching.